Hello. The purpose of this video is to give you a pretty thorough introduction to the concept of infinite sequences. Okay. All right. So, what is a sequence? A sequence is a list of numbers, or sometimes even functions. But for us in this class, we will only deal with list of numbers. So for us, a sequence will always be a list of real numbers. All right, and maybe an informal definition of a sequence could be the following. A sequence is an infinite list. It's an infinite list of things, really real numbers. Such as let's say 1, 2, 3, 4, and so on. So this is, and so on. So this keeps going. This is like a counting number. It keeps going indefinitely. But let me finish the definition here, which are written in a definite order. From first to last. Only thing here is there's really no last, because we keep going all the way till infinity. There is, for us, we keep going indefinitely, so we'll say forever. For last for us here will be forever. So as an example, one half, 1/3, 1/4, 1/5, 1/6, 1/7, and so on. Right, this is an example of a sequence of real numbers, and the three dots here are ellipses, and this means that the list goes on forever. Here's another example. -1, 1/2, -1/3, 1/4, -1/5, 1/6, -1/7, and so on. And this is an example of an alternating sequence. We could have 1, 1, 1, 1, and so on. And this is an example of a constant sequence. We could have 1, 2, 3, 4, 5, 6, 7, 8, and so on. And this is an example of sequence which consists of the counting numbers. So you just count. We could have 2, 0, 2, 0, 2, 0, and so on. We could have 1, -1/3, 1 over 9, negative 1 over 27, and so on. And this is a geometric. This is an example of a geometric sequence. Here you can see here that the denominator are powers of 2. I'm sorry, of 3. All right. Now let's quickly review the our notation for sequences. So notation for sequences. First, we can have what we call a list notation. And in this case, for a list notation, we simply just list the element 1, 1/3, 1 over 9, 1 over 27, and so on. The first one is called a sub 1. The second one is a sub 2. So a sub 2 is 1/3. A sub 3 is 1 over 9. A sub 4 is 1 over 27, and so on. So we pronounce as, this one here is pronounced as a sub 1. And we say that a1 is the first term. A sub 2 is the second term, and generally a sub n is the nth term of the sequence. Okay. We can also have another kind of method for presenting a sequence. In this method, we use a formula. We use a formula notation giving the nth term of the sequence. So, for example, I could tell you that a sub n is 1 over 3 or power n minus 1, or in other words, a sub n is really 1 over 3 power n minus 1. And in this case, you know that a sub 1 is 1, a sub 2 is 1 over 3, a sub 3 is 1 over 9, a sub 4 is 1 over 27, and so on, right? So this is a list notation, and this here is a formula notation. All right. Those are the two general notations that we use for sequences. But sometimes I will write, once you have a sequence which is given to you in the formula notation, we'll write the sequence as follows. A sub n is running from 1 all the way till infinity, is the sequence whose nth term is given by 1 over 3 power n minus 1. Okay. And of course, a sequence could be given without. Sometimes it's impossible to have a formula for a sequence. Maybe you could have a sequence which is given to you recursively, right? So we can have a recursive sequence. Sequence which may take the following form. Let's say a sub 1 is equal to 1, and generally I would say that a sub n is going to be square root of a sub n minus 1 plus 1. Right, so in this case, the first term a1 is 1, of course. The second term a sub 2 is given in terms of the first one, so it will be a sub 1 plus 1. which is 1 plus 1, which is square root of 2, and then you may have a sub 3, which is given to you as a sub 2, square root of a sub 2 plus 1, and that will be square root of 2 plus 1, and a sub 4 is square root of a sub 3 plus 1, which will then be square root of the square root of 2 plus 1 plus 1, and so on, right? And you can keep going in this fashion. So you can have a sequence which is also given this way. And one may be interested also in visualizing or graphing a sequence. So how do we graph a sequence? Graphing sequences. There are two ways for generally to graph a sequence. You can graph a sequence as a one-dimensional plot along the real line. Alright, so in this case, suppose you are given, for example, a sub n is equal to 1 over n, where 1 over n is the nth term of your sequence. Then one way to graph the sequence is to maybe consider these sequences as essentially numbers on the real line. So when n is 1, then you get a sub 1, which is 1, and let's suppose 0 is somewhere here. 0 is not the term of our sequence, but let's suppose 0 is located somewhere there. When n is 2, then a sub 2 is 1/2, a sub 3 is 1/3, a sub 4 is 1 over 4, and so on. And you can see that your sequence is getting closer and closer to 0, but will actually never arrive to 0. So 0 is not a member of is not a term of this sequence. 0 is not a term of the sequence, but the graph of this sequence shows that it's getting closer and closer to 0. We can also sometimes use a two-dimensional graph instead. So we could have Alright, so in this case, then let's say we regard we regard an the sequence as a function over the natural numbers. And what this means is that, so we have 1, 2, 3, 4, 5, and so on. These are the natural numbers or counting numbers, and we'll look at, suppose if an is equal to 1 over n again, then a1 is 1. So suppose this is 1. Then this is the first term of our sequence. A2 is let's say 1/2. So that's the second term of our sequence. A3 is 1/3. So this is 1 over 3. 1 over 4, and so on, right? So you can see again, you can visualize here our sequence as a sort of a discrete graph, and this should remind you, this graph reminds you probably of the graph of y is equal to 1 over x in the first quadrant. So you can regard this as a discrete version of the graph of y is equal to 1 over x. All right, so next let's look at some more other concrete examples. So for the first example, we like to find a formula for the general term an of the sequence, assuming that the pattern of the first few terms continues. And to this end, right, so for the first example, suppose we have 1, negative 2/3, 4 over 9, negative 8 over 27, and so on. So you can see that the numerators are powers of 2, and the denominators are powers of 3. Okay. All right, so also we see that the minus sign alternate and is seen with even number terms. Such as A2, A3, A4, and so on. Okay. All right. So the first, you can think of the first term here is a power of 2. So you can write 1 as some power of 2, right? 2 power 0, I guess, over 3 power 0. But I'll come back to the sign for now. You can write 2, negative 2/3, as negative 2/3 power 1. And then you can write 4 over 9 as 2 over 3, right, square. And then you can write negative 8 over 27 as negative 2 over 3 cube. All right, so note again that this is the first term. This here is the second term. This is the third term, and this is the fourth term. All right, now to alternate the signs, the way to fix this is to put a negative here and to regard this as really as this as being negative 2/3 power 0, and this will be negative 2/3 power 1, and this is negative 2/3 square. It won't change anything because the square of a negative number is still square, and so on. So generally then it seems that if this pattern keeps going forever, then the nth term of our sequence a sub n will have to be negative 2 over 3 power of something. Notice that the first term is power 0, the second term is power 1, the third term is power 2. So it's always 1 less than the index of the sequence. So it will be power n minus 1. So generally we have that the nth term of our sequence is that. All right. Take your time to check to make sure that you follow what this discussion and that you can recreate it on your own. Now next, consider this sequence here: negative 1 over 4, 2 over 9, negative 3 over 16, 4 over 25, and so on. Again, we notice that the numerator for the numerator is equal to the subscript of the ANs, and the denominators are perfect squares, right? They are perfect squares of 2, 3, 4, 5, and so on. And then also here the minus sign alternate, and is seen with odd numbered. It's seen with odd numbers terms, A1, A3, and so on. Okay, so then we to guess, we can see maybe that, okay, so we want to guess what the nth term of the sequence will be. Well, the numerator must have n in it. The numerator must have n in it. The denominator, right, the first one is 2 square, the second one is 3 square, and so on. So the nth one will be n plus 1 square, and the sign is alternating, right? So it should be negative 1 power something. Well, let's see. If I set this to be negative 1 power n, if n is equal to 1, then the first one will be odd, and the second one will be even, which will be 1. The third will be negative 1, and so on. So this will be power n. So we see that the nth term of our sequence should be that. And again, you should definitely check your work and make sure that all of this makes sense to you. Now, generally, we note that negative 1 power n is going to be this sequence. N is odd, so n is equal to 1 is odd, so we get negative 1 first, and then 1, negative 1, 1, negative 1, 1, and so on. And if you have negative 1 power n minus 1, if n is 1, we get 0, so it will be 1, negative 1, 1, negative 1, 1, negative 1, and so on. And negative 1 power n plus 1, if n is 1, we get 2, so negative 1 square is 1, negative 1, 1, negative 1, 1, negative 1, and so on. Okay, so generally, this is the behavior that we have when you are taking powers of negative 1. All right, so now we'll look at the concept of divergence and convergence. Limit of sequences convergence and divergence. All right, so first, if we consider the sequence an, which is 1 over n, we saw that this sequence looks like 1, 1/2, 1/3, 1 over 4, and so on. And you can see here that as n is growing without boundary, the distance between 1 over n and 0 is getting smaller and smaller. So we say that the limit as n is approaching infinity of 1 over n is equal to 0, and we say that the sequence 1 over n, when n is going from 1 to infinity, is a convergent sequence.
Daddy, I got your pie for you. I have your pie for you, Daddy.
Now, let's consider another sequence an, which is equal to 2 power n. Have 2 square, 2 cube, 2 power 4, and so on. And you can see that as n is growing without boundary, 2 power n is getting larger and larger, and we say that the limit, as n is approaching infinity of 2 power n is going to be infinity, and in this case we say that the sequence 2 power n, when n is going from 1 to infinity, is divergent. All right, so the concept of convergence allows us to say that a sequence, the term of a sequence, is getting closer and closer to some numbers. And if we can prove that, then we'll say that the sequence is convergent to that number. Otherwise, if that doesn't happen, then we'll say that the sequence is divergent, or the sequence diverges. All right, so let's look at another example. Let's consider the sequence an, which is -1 power n, right? And you can see that this sequence is -1, 1, -1, 1, and so on. And if you were to plot the terms of this sequence over the natural numbers, if this is 1, 2, 3, 4, 5, 6, and so on, you know, n plus 1, then a1 is -1, a2 is 2, a3 is -1, a4 is 1, a5 is -1, 1, -1, and so on, right? So this keeps jumping back and forth in between 1 and -1. So clearly this sequence does not converge to anything. So we'll say that the limit, we shall say that the limit of this sequence, the limit of an as n is approaching infinity, does not exist. Okay, so in conclusion, when it comes to the concept of convergence and divergence, we say that a sequence is convergent when the limit is a single number. And we say that the sequence is divergent when the limit is either plus or minus infinity, or it does not exist, like in that last case. All right, so let's look at a few cases where we get to evaluate some limit. First, I will consider let's consider one simple example. Let's see. We want to compute the limit as n is approaching infinity of 3 plus 7n square over n plus n square. Okay, so in this case, notice that the numerator is going to infinity and the denominator is going to infinity, and then you have a ratio of two arbitrarily large numbers. It's not clear what that may be. So we need to work a little harder to determine what can be done here. And what we'll do here is we will factor the term which is the dominating term out of each one. So let's say n square. We factor n square out of the numerator, so we get 3 over n square plus 7 over, and then factor n square out of the denominator, so we get 1 over n plus 1. And clearly these two will cancel each other out, so we'll have the limit as n is approaching infinity of 3 over n square plus 7 over 1 over n plus 1. And then clearly this will go to 0, right? And then this will go to 0 as n is getting larger and larger, so we'll get 0 plus 7 over 0 plus 1, which is 7. Okay, so this sequence, the sequence 3 plus 7n square over n plus n square, when n is going from 1 to infinity, is a convergent sequence. Okay, all right, so let's consider another example. Let's consider the limit as n is approaching infinity of the natural log of n square over n And as we know, so first, perhaps it makes sense to simplify the natural log of n squared first and to write it as 2 times the natural log of n over n, and as n is approaching infinity. So L'Hopital's rule tells us, because the numerator is going to infinity and the denominator is going to infinity, we may appeal to L'Hopital's rules and we take the derivative of the numerator. Right, so we get 2 over n, and then the derivative of n is just 1. So this will be equal to the limit as n is approaching infinity of 2 over n, which is going to be, of course, 0. By so here we use L'Hopital's rule here to handle this limit. So to remind you of L'Hopital's rule, maybe you forgot what L'Hopital's rule is all about. So remember that L'Hopital's rule says the following: if f of x, if the limit as x is approaching infinity of f of x is equal to plus or minus infinity, and the limit as x is approaching infinity of g of x is equal to plus or minus infinity, then the limit as x is approaching infinity of the ratio f over g will in fact be the limit of f prime of x over g prime of x as x is approaching infinity. Okay, all right, so this is what L'Hopital's rule is all about. Next, let's consider the limits as n is approaching infinity of 2 power n, 3 power n plus 1. And notice that this will be the limit as n is approaching infinity of 2 power n over 3 times 3 power n. And we can pull this 1/3 out. So we get 1/3 times the limit as n is approaching infinity of 2 over 3, the whole thing power n. All right. Now remember that if y is equal to ax, then this is equivalent to the fact that natural log of y is equal to the natural log of ax, which is really x times natural log of a. Now exponentiating each side of this equation gives us that e power natural log of y is going to be ex natural log of a, and this really means that y is equal to ex natural log of a. So, and this is a good formula to be aware of. So then we can rewrite, if I call this here star, we may rewrite star as 1/3 times the limit as n is approaching infinity of en times the natural log of 2/3. Now, since 2/3 is less than 1, then the natural log of 2/3, as we know, will be less than 0. So it's a negative number. Remember that the natural log, the graph of the natural log looks like this, where this is 1. So for any number which is less than 1, its natural log will be negative, right? So this thing here that we're looking at is a negative number, and as n is getting bigger and bigger, so all of this here will be extremely big. So this is diverging to infinity. This is diverging to negative infinity. So the exponential of a big number in absolute value but with the negative sign will be 0. So you get 1 over 3 times 0, which is 0. So thus the limit of 2 power n over 3 power n plus 1 as n is approaching infinity is going to be 0. And again, let me run this argument one more time. The point being that if you look at the graph of the exponential function, this is y is equal to e of x. When x is tending to negative infinity, e of x will go to 0, right? So since natural log of 2/3 is negative, this thing here is negative. It's going to negative infinity, so e of a huge number is getting closer and closer to 0. So that's where this is coming from. All right, so to summarize, actually this example leads us to a nice theorem which can be stated as follows. Let C be a constant. Then three things are possible. Suppose, let me say that let C be a positive constant. Let C be a positive constant. Then the limits of C power n as n is approaching infinity will be equal to 0 if C is a number in between 0 and 1. It will be equal to 1 if C is equal to 1, or it will diverge to infinity if C is greater than 1. Right? So if you're looking on the number line, and this is 0 and this is 1, if you pick your C, if you pick your constant here and you look at powers of Cn, this thing here will go to 0, while if you of course pick C to be 1, then 1 power n is always going to be 1, so you just get the constant function which is 1 everywhere, so it will converge to 1. However, if you pick your C to be here such that it's greater than 1, then as n is getting bigger and bigger, C power n is going to diverge to infinity. So as an illustration, we can then say that the limit of 1/2 power n when n is approaching infinity is going to be 0, since 1/2 is a positive number which is strictly less than 1. On the other hand, notice that the limit of 2 power n when n is approaching infinity would be infinity, since our constant here C is bigger than 1, and of course the limit of 1 power n as n is approaching infinity is just going to be 1. Next, our next theorem will help us handle taking limits of a sequence with powers of -1. Let's an be a sequence. Then the following holds true. If the limits of the absolute value of an as n is approaching infinity is equal to 0, then the limit as n is approaching infinity of an will be equal to 0. Notice that we didn't say that if the limit of an is equal to 0, then the limit of the absolute value of an will be equal to 0. This is saying that if the limit of an absolute value of a sequence goes to 0, then you can automatically conclude that the sequence itself must converge to 0. Okay. So perhaps we could start with an example here, and our first example will be the following. Let's compute the limit of a -1 power n over n as n is approaching infinity. We want to know what this thing is, and to this end we will first compute the limit of the absolute value of -1 power n over n as n is approaching infinity, And as you know, this will be the limit of negative 1 power n over absolute value of n as n is approaching infinity, and this is the limit of 1 over n as n is approaching infinity. And the reason of that is because so this thing here will be either plus or minus 1, right? And the absolute value of plus or minus 1 is 1, of course. And this thing here is positive, so it is equal to its absolute value. When a number is positive, that number is equal to its absolute value. All right, so and then we know, of course, that this will go to 1 over n goes to 0. So since the limit of the absolute value of the this sequence is going to 0, we conclude that the limit of negative 1 power n over n as n is approaching infinity must be 0. And it seems so. Maybe a picture will also help here, convince us that we're on the right path. If we consider this the sequence negative 1 power n over n, when n is 1, then we get negative 1, right? So we're somewhere here. When n is 2, we get 1/2. When n is 3, we get negative 1/3, and so on. So the sequence is sort of alternating, it's jumping back and forth, but each time it's getting closer and closer to 0, right? The distance between each term is getting closer and closer to 0 as n is getting bigger and bigger. So it does make sense that that the sequence will converge to 0, right? So this is an example of an alternating. This is an alternating sequence which is convergent. All right, so let's look at another example. Let's consider we consider the limit as n is approaching infinity of negative 1 power n minus 1 times n over n squared plus 1. So first, let's compute the limit as n is approaching infinity of negative 1 power n minus 1 times n over n squared plus 1. The limit of a ratio is a ratio of limits, so we get negative 1 power n minus 1 times n, absolute value of that, over n squared plus 1, absolute value of that. And again, notice that this thing here is positive, so we can safely remove the absolute value. And then moving forward, we get the limit of negative 1, absolute value of negative 1 n minus 1 times absolute value of n over n squared plus 1 as n is approaching infinity. And again, n is positive, right? This is positive, so we can remove the absolute value, and this thing here is negative 1 or 1, so its absolute value will be 1. So in the end, we obtain the limit as n is approaching infinity of 1 times n over n squared plus 1, which is the limit of n over n squared plus 1 as n is approaching infinity. And we'll play the same game we played earlier. I will factor n squared out of the numerator, so we get 1 over n. And then we factor n squared out of the denominator, so we get 1 plus 1 over n squared. And we compute the limit of this by crossing out the common terms. and we get 1 over n over 1 plus 1 over n squared. And as you know, the top will go to 0 and the denominator will go to 1 plus 0 as n is getting bigger and bigger, so we get 0. And this is a good news for us because we can then appeal to the previous result. So by the previous theorem, the limit of negative 1 power n minus 1 times n over n squared plus 1 as n is approaching infinity will be 0, because the limit of its absolute value is equal to 0. Alright, so we will now look at another interesting example, which is the following. We consider the limit of negative 3 power n over n factorial as n is approaching infinity. So you may not maybe remember or know what n factorial is. N factorial, which is read n factorial, is simply the product n times n minus 1 times n minus 2 all the way till 3 times 2 times 1. Okay, so this is just a product. N factorial is a product of a countdown from n to 1. From n to 1. So for example, 5 factorial is 5 times 4 times 3 times 2 times 1, and that's 120. And 4 factorial is 4 times 3 times 2 times 1, and that's what's 12 times 2, that's 24, and so on. So although 0 is not defined, 0 factorial is not defined this way, in this fashion, we will define 0 factorial to always be 1. Okay, so all right, so so this is what the factorial is all about. And now we would like to compute the limit of this thing as n is getting bigger and bigger, and we will appeal to the previous theorem and see whether the previous theorem can help us, right? So the previous theorem tells us that if we can prove that the limit of the absolute value of the sequence goes to 0, then that sequence must be going to 0. Again, this is an example of an alternating sequence. So if its absolute value goes to 0, that means that each term is really getting closer and closer to 0 as n is getting larger and larger, and that will mean that the sequence goes to 0. But we need to prove that. Okay, so how do we do that? All right, so for this purpose, let's look at the limit as n is approaching infinity of the absolute value of negative 3 power n over n factorial. And of course, this will be the limit of negative 1 power n times 3 power n absolute value over absolute value of n factorial as n is approaching infinity. And you know that this thing is always positive, so we can remove its absolute value. It's just n factorial, and this will be absolute value of negative 1 power n times 3 power n, because 3 power n is also positive. And again, since negative 1 power n is plus or minus 1, its absolute value is always 1. So this ends up being the limit as n is approaching infinity of 3 power n over n factorial. All right, so now we need to understand what is really happening here. So to this end, we'll do some analysis. expand this 3 power n out, right? So this is 3 times 3 times 3 times 3 n times over n factorial, which is n times n minus 1 times n minus 2 times 5 times 4 times 3 times 2 times 1. And I will rewrite this out as the limit as n is approaching infinity of 3 times 3 times 3, and I'll have two 3's left out here. And here I will have n times n minus 1 all the way till 5 times 4, and I will have here 3 times 2 times 1 left out here. And of course you can see that this will cancel each other out, and this thing here will just be 9, and this will be 2. So we get here the limit of 3 power n minus 3, right? Because you are multiplying n by itself, n minus 3 times here. This is n minus 3 times, and this is by itself 3 times, so that you get a total of n times. So there's so after you this product here will be 3 power n minus 3, and then the bottom is n times n minus 1 all the way till 5 times 4 as n is approaching infinity, and then you have time 9 over 2. 9 over 2 is a constant, so I'll move this out. So we get 9 over 2 times the limit as n is approaching infinity of 3 power n minus 3 over n times n minus 1 times 5 times 4, and so on, right? So the one thing also to be aware of is that these tricks is going to work for us if when we observe that every single one of these factors, each factor is larger than 3, right? So what we have is a bunch of numbers which are very large. Each one of them is larger than 3 here, and then as n is getting larger and larger and larger, the numerator is getting bigger and bigger, and the denominator is getting bigger and bigger. However, it's growing to infinity much faster than the numerator is going to infinity. So this thing here will go to 0. So we'll get 9 times 2, 9 over 2 times 0, which will be 0. All right. So let me try to explain again why this quantity must go to 0. You have each time you have 3 times 3 times 3, n minus 3 times, and you also have n minus 3 factors on the denominators, right? And here they are, all the factors here are all 3's, while all the factors on the denominator here, you have as many, you have n minus 3 of them, but they're all bigger than 3. So as n is getting larger and larger and larger, the denominator is going to dominate the numerator, and then this ratio will get smaller and smaller and smaller, and you eventually get 0. So then by our previous result, by our previous theorem, we conclude we conclude that the limit of negative 3 power n over n factorial as n is approaching infinity is going to be 0 because its absolute value goes to 0. Now, let me give you a theorem which essentially summarizes or generalizes these ideas. The theorem is stated as follows. Let C be a constant and P some positive numbers. And C is also, by the way, C is also positive. Then no, we don't need C to be positive necessarily. Sorry. Then the limit as n is approaching infinity of C power n over n factorial is going to be 0, and the limit as n is approaching infinity of n power p over C power n is also going to be 0. And the thing to observe here is this here. The numerator here is exponential, and the denominator is factorial. And the points here is that a factorial grows faster than an exponential function, which is the reason why this ratio goes to 0. Similarly, you can see that the numerator of the second sequence is a power, it's n power p, and the denominator is an exponential. And it is a fact that an exponential function grows faster than a power function, and as a result this sequence here will converge to 0. So an illustration, so again, to summarize, a factorial outgrows an exponential, and an exponential outgrows a power. Okay, so a factorial outgrows an exponential, and exponential will outgrow a power. And as an illustration, then one can then, for example, if given the sequence, let's say 2 power n over n factorial as n is approaching infinity, one can conclude that this must be 0 because the numerator is a power and the denominator is an exponential. The numerator is an exponential and the denominator is a factorial. So from part A we get 0, and if you are considering the limits of, let's say, n power 100 over 2 power n as n is approaching infinity, this thing here, so the numerator is a power and the denominator is an exponential, and then of course you'll get 0. Alright, so we have reached the end of our lesson. I hope this presentation was clear and that you were able to follow my argument. Thank you for listening, and I hope you show up for the next video. Bye bye.